First, let me thank the organizer for inviting me to give this talk here. The topics of this lecture will be a little bit different from what you have heard so far. I'm going to tell you about non-relativistic conformal field theory. Hopefully I will cover some basic theory and possible, some application, at least one application of non-relativistic conformal field theory. Can you hear me in the back?
Yes.
Good. Okay, so
if you can speak up
a little bit. Yeah. Yes. So first, references. I'm going to cover some material in an old paper by Yusuke Nishida and myself. And you can find it's around 0.7, etc. And then one thing I hope to cover is a recent application to nuclear physics that Hans Hammer and I did. It's already, I think, 2103. So before we start with conformal field theories, let us review the non-relativistic QFTs. Okay, so the simplest one first. Let's consider the action of a theory that is described by the following action. Psi dagger. So let me write this way. D psi psi minus grad psi square over 2m. This is a simplest non-relativistic field theory. The field psi here can be bosonic and can be fermionic. Let me not specify it right now. Let's assume it to be bosonic for simplicity first. So what we can say about this theory is that the equation of motion has the form of dt psi is equal to minus grad square psi, if I'm not mistaken with the sign. This is the usual Schrödinger equation. Of course, the Schrödinger equation is usually thought of as an equation for the wave function of a single particle, but in field theory, psi is operator. And this description appears somewhere in the course of quantum mechanics when one discusses second quantization. So this field psi would be the operator that annihilates the particles. So if I quantize this theory, I have to first impose the commutation relations, which in this case is psi x psi dagger of y is equal delta of x minus y. Basically, the momentum canonical conjugate to psi is psi dagger, so that's why we have this commutation relation. And we can, for example, expand psi in plane wave, as usually we do. So let me notice here that d in my talk will be going to be the number of spatial dimension, not space-time, but the number of spatial dimension, and then I have here e to I kx with some time a of k. One specific thing that we need to get used to in non-relativistic field theory is that the expansion of the operator psi contains only annihilation operator, but there is no creation operator. It's something that probably we have to unlearn from relativistic field theory. So psi of x acting on the vacuum always will be 0 in our non-relativistic field theory. If there is any question during the talk, please interrupt me at any time. Okay, so now
can you explain why?
Why?
Why only animation operator?
Appear? So you can see it in various ways. So one way is to say how do I satisfy this commutation relation. Usually in relativistic field theory you have to satisfy the commutation relation. In addition to that you want causality, Lorentz invariance. So that's why the expansion of a field operator in relativistic field theory necessarily would have both creation and annihilation operator. The way that we usually come up with this field theory in quantum mechanics is we want to write down a field theory that can simultaneously describe quantum mechanics of one particle, two particle, three particle, etc. by one single theory. And that's the description usually called second quantization. And in the field and the form of the action, we have this kind of action. Okay.
Is there a notion of causality here in this?
There is only a notion of there is no light cone. So the if you take the commutator of two fields, so this is at the same time. This is the commutator at the same time, and it has the form of the delta function. But if one take the commutator of two fields at two different times, you'll see that it's non-zero. There's no light. There's no light cone. It's generically non-zero. Okay, so this is a free field theory, and it's rather boring in the sense that we can understand the full Hilbert space of this theory, all the energy eigenstate. The energy eigenstate are just a state that we get by acting the creation operator AKN on the vacuum. And depending on whether we deal with the bosonic or fermionic particle, we may have to symmetrize or anti-symmetrize this state. And then the energy of this state is simply sum of Ki squared over 2m. The superposition of plane wave would be an eigenstate of the non-relativistic theory. So, to be a little bit less boring, let me add to this Lagrangian an interaction term. So I will write minus C psi Decker, psi psi. And again, for simplicity, let's consider psi to be C over 2. Let's do C over 2. Assume psi to be bosonic for a moment. So that would be the non-relativistic version of the 5-4 theory. That would be the simplest interacting field theory in a textbook. So the first thing we would like to determine is whether this interaction term is relevant or irrelevant. And for that we need to do a power counting. So the power counting in a non-relativistic theory like this, to be consistent, we have to assign different dimension for space and time. So let's first talk about this mass m first. So as we will see later on, this mass is something that is just a constant, like the constant of the speed of light in non-relativistic theory. Here m is just a translational factor that translates between momentum and energy. So the m should be considered as something at dimensionless. Derivative with respect to space, if we assign dimension 1, then derivative with respect to time have to be assigned dimension 2. Right. Space then has dimension -1. This factor has dimension -d. This has dimension -2. And if you require that the action is dimensionless, the dimension of psi then is equal d over 2. Again, d is a number of spatial dimension. then this term and this term would have the same dimension of d plus 2. And we integrate over the whole space-time. We get dt dx, we get dimensionless action. The dimension of this operator has to have dimension equal d plus 2. But the dimension of the fourth particle interaction phi 4 term is 2d because it contains 4 factor of psi. So the dimension of the coupling constant C is equal to 2 minus d. From that we find that this theory, the interaction, the 4-point interaction behaves differently when the dimension of space is less than 2 or bigger than 2. And there is a marginal case of d equal to 2. If d is less than 2, then we have the Decker psi square term is relevant. If d is equal to 2, this term is marginal. And if d is larger than 2, this term is irrelevant. We will be mostly interested in the case of d equal to 3. But for a moment, let's consider the case that seems to be more interesting here, that the case of d equal to 2, when the interaction is marginal. And ask what happens when we have particles interacting with a point-like interaction, this psi to the 4th term, in 2 plus 1 dimension. Any question so far? Yeah.
Could you explain why the mass is dimensionless?
When the mass is dimensionless, so running ahead, I will, some point we will talk about the Galilean symmetry of the theory. We'll see that m is just a parameter that is fixed in the Galilean transformation. That means that m cannot be renormalized. At the level of more naive reasoning, here we just, if we just say m plays the same role in this formula as the speed of light in the formula E equal c times k. So we can set c equal to 1 in the relativistic theory, and so here we just set m equal to 1. A more interesting reason would be that this m actually is not renormalized because it's related to the Galilean symmetry.
So if I have two different species with different m, they both don't renormalize.
When you have two different set of two different m, then there is a mass that is conserved. So there is one conserved quantity, that is the m1 times the number of particles of type 1 plus m2 times particle number of type 2.
Is there a simple way to obtain this theory from relativistic QFT in the non-relativistic limit?
Sure, you can. So you take a phi 4 theory and phi 4 complex scalar field theory, for example, and then you look at the sector of the theory where the energy is just slightly above the threshold of creating n particle. Right? So you take these, we just basically take the non-relativistic limit of relativistic field theory. So you look at the kinematic region when the particles are all have very low energy, and then that will be this theory.
Right, but that I get a boson, right? Because you said this phi can be either boson or fermion. But from the relativistic one, I would have first order kinetic term of fermions.
Well, we can have a boson. So it's like O2 model, a model of scalar with an O2 symmetry or complex scalar field. And then, so let me say it this way. Let's take a theory like Lagrangian equal d mu phi right, minus m square phi square. And the way we can go to this limit is to include in the theory a chemical potential, mu. So in Lagrangian would be mu phi square. and then take mu basically close to chemical potential would be like this. So take, should I go that or let me just say in physical term what happening. So the operator phi phi is an operator that annihilate particle or create an antiparticle. If I now look at the sector of the theory where the energy minus m times the charge q is much smaller than the mass times q, that's the non-relativistic sector of the theory. In this sector, one can show that the theory reduces to that theory. Yeah.
I guess the people are confused. What is the relation between phi and psi? Phi, for example, here you have two derivatives, and there's a one time derivative.
Was that that was the confusion? Okay, so the translation is the following: you have phi is equal to e to I m minus I m t psi divided by square root of 2m. So here's what happening is that in this non-relativistic limit, the function phi has a fast phase rotation in time, modulated by a function that is smooth in t. So this function psi varies in time over a distance that is much smaller, much larger than 1 over m. Yeah. So when you substitute that one here, and then omit in the Lagrangian old term that has very fast phased oscillation, in phi you get back this theory. Yeah.
Sorry, excuse me. Why does time have mass dimension too?
When is time once we have go from this relativistic theory to a non-relativistic theory, right? Now I'm going to try to develop a power counting. If I want to develop a power counting that allows me to tell whether this interaction is relevant, irrelevant, or marginal, I have to make sure that this term and this term count in the same way. All right. So the mass I can set to 1, for example. If I set the mass to 1, in order for this and this to have the same dimension, the derivative with respect to time has to have the same dimension as second derivative in space. And that will be important when we talk about the scale invariance in the theory. What kind of scale invariance? Yeah.
So here the analysis for the dimension counting is based on like a perturbation around the 3 fixed point. And suppose I consider a larger, maybe larger phase diagram, so that perhaps either UV or IR, maybe one of them is relativistic and the other is non-relativistic. Is it possible to maybe argue the total dimension of the dimension of the time derivative of space derivative, how does it change? Suppose there are some flow between relativistic and non-relativistic or vice versa.
There may be such a flow, but we are not going to consider it here. So I'm going to consider only the flow between 2 fixed points. Both of them are non-relativistic, and both of them turn out to have this relationship between derivative in time and space. So sometimes we call that z equal to 2. Both fixed points we call z equal.
Asking in case maybe you have a comment, say suppose I want to run between, say perhaps more UVC is non-relativistic as this counting, and IR is relativistic. How should I think about this dimensional counting when they change?
I have no comment. Yeah, because I haven't thought about that, to be honest. Yeah. Okay, so that's, I think this really a psychological barrier for us. We have lived in a relativistic world for so many years, and now going back to non-relativistic world can be some facts might be not very intuitive. Okay, so let me now go into some calculation. So in order to see whether this interaction at d equal to 2 is marginally relevant or marginally irrelevant, we have to compute the beta function. So we sketch how the calculation of beta function looks like. And on the way, we will see some facts about non-relativistic field theory that simplifies a lot of calculation. First of all, the Feynman rule of the theories are the following. The propagator of a single particle is associated with the functions. That is a function of omega and p. Omega is for frequency, p is the momentum, and that is I divided by omega minus p squared over 2 plus I epsilon 2m. So it restores the mass. But the mass can be something that really can be set to 1 if we want to. And then the second Feynman rule is that the interaction vertex, I think, is minus 2IC. So one thing about this G is that the green function in non-relativistic theory is retarded. That is, if I now Fourier transform back to space, G of t of x, you can show G of t of x is equal to 0 if t is less than 0 and is non-zero only when t is larger than 0. And we can see that in various ways. The straightforward way is to Fourier transform this green function. So this green function has a single pole in the lower half plane. And if t has a wrong sign, we can close the contour to the upper half plane, and we see that the green function would be 0. That's one way of seeing that this green function has to be 0 when t is less than 0. Another way to see the same thing is to remind ourselves that in field theory, the green function is the expectation value of the t product of psi and psi Decker, 0 and 0. So here expectation value means we take average of the time order product between the vacuum. If time order is such that time is larger than 0, this is non-zero. But if time is less than 0, time order product means that we have to take the operator psi Decker and put it in front of the operator psi. And we have already said that the operator psi acting on the vacuum is 0, because in non-relativistic field theory, the operator psi contains only annihilation operator. And so what is interesting, would be very specific for this kind of non-relativistic field theory is that the propagator is retarded. That's no 0 if it goes backward in time. And that simplifies a lot of diagrams. So for example, if we look at the normalization of a single particle propagator, usually in relativistic theory, we'll have to sum up diagram like this. Right. This would be, in phi-4 theory, that would be a one diagram that contribute to the green function. So for example, let me draw the arrows. So the vertex should be such that there is always 2 arrows coming in, 2 arrows coming out. So for example, this diagram, this vertex is the correct one because we have 2 arrows coming in, 2 coming out. But right away we will see that this diagram is 0 because it contains the product of 3 different propagator. 2 of that is gxy and the other is gyx. And one of these propagator has to be 0 because the time order in one of them should be the reverse. Either x0, the time of x, larger than time of y, or the other way around. this product will always be 0. So the self-energy is always 0.
Well, what's xy? Because you were denoting t and x, and now
Yeah, so it's x without the vector index would be this x. So it contains both time coordinate and x coordinate.
like x minus y, then, or whatever.
Yeah, whatever. So the more correct thing, let me write g of tx minus ty, right? And x minus y square times g of ty minus tx y minus x. That is the other operator that's coming out here, and you see that it's always 0. So a single particle in non-relativistic field theory can propagate with the bare propagator. Any interaction in non-relativistic field theory will not modify the propagation of a single particle.
How do you take care of equal time? What do you assign the propagator at equal time?
We can assign it to be half, for example, but when we integrate, it's just 1 point. And so,
Like, what is the usual assignment in the 2-point function?
but the usual assignment, it's not very important whether you assign it to be half or you can assign it to be 1/2 at that point. Because it's always, you need to do an integral, and that single point usually doesn't contribute to anything. Yeah.
So in that diagram, you have to integrate over the position of the vertices.
Yeah.
So the propagator is 0 everywhere, but maybe there are some, when 2 points come together, there's a divergence, or you might have a contact term.
Might.
And that might change the result, but the diagram is non-zero.
In principle, it might be like that, but for this particular things, you can compute the propagator, and you see that it doesn't have a delta functional singularity. It has the propagator here in coordinate space simply has a jump at t equal to 0. So it's more like a function that looks like this, rather than, yeah. Mm-hmm.
So this is consistent with this mass not being normalized. That does it also mean that phi doesn't acquire a normal dimension?
It doesn't for a very simple reason. So let's go back to what we wanted. Yeah, maybe I answer this question. What do we want to describe in this theory? Basically, here we are trying to describe to write down a field theoretical description of a collection of particles interacting with each other through delta functional potential. So basically, if we go back to the first quantized language, we will write the Hamiltonian equal to sum of the Hamiltonian of all particles plus the plus C naught sum over delta function xi minus xj and I less than j as the potential of interaction. Now, we have quantum mechanics description. We see right away that if we have just one particle, it cannot interact with anything. It just propagates by its own. Non-trivial scattering happens only when you have 2 or more particles. That's why physics of a single particle is there's no bubble. In the relativistic theory, this bubble appears in the jargon. At least we think of creation of particle-hole pairs out of the vacuum. Here, such thing doesn't happen in non-relativistic theory.
Is the C not positive or negative, or you consider both?
We'll consider both. Yeah. There was a question.
Is that why you don't include the one loop diagram?
The one loop diagram. Yeah, this one loop diagram like this. Like this one. Yeah, this one loop diagram is actually coming from the fact that I have time or normal order my interaction. So if I order the interaction slightly differently, the result will be simply a shift of a chemical potential which I set to 0. In principle, we can also include a term like mu to psi Decker psi in the Lagrangian. I set it to 0. That corresponds to a zero chemical potential in that case. The interaction I've written so that all the operators psi Decker stay on the right and the psi on the left. So that term is 0. Now, if I'm now trying to look at the renormalization of the 4-point interaction, we know how to look at this in 5-4 theory. Relativistic 5-4 theory would have to compute one loop diagram. So these are the diagrams that usually we would think of as the diagram that renormalized interaction in 5-4 theory. And there is one more diagram, it's S channel, T channel, and U channel. I'm not going to drop the U channel. So in non-relativistic theory, we have to draw, this is the first one loop correction to 4-point vertex. Second correction is this one. Okay, so here I have to make sure that there's one coming out, one coming in, coming out, and coming in. Right, all the vertices are correct number of lines that come out, come in. But here we have a closed loop, that is one propagator going from one point to the other, and the same propagator going. So both of them cannot go forward in time. One has to be backward in time, and this is 0. And then this is the only diagram that contribute to the beta function. Any question so far? Okay, so computing that, I'm not going to do that in real time. I'm going to tell you the result of this calculation, the beta function. So in d equal to 2, the beta function of c is equal to c squared over 2 pi. So the solution to the renormalization group equation, c as a function of lambda, log lambda is equal to beta c, with the boundary condition c is equal c0 at, say, lambda equal lambda 0, is the following. So let me write it here. C is equal c0 divided by 1 plus c naught over 2 pi. A lot of formula looks very familiar. Lambda naught over lambda. Okay, so this is the one can think about this lambda naught, for example, as a UV cutoff in the theory. C naught would be a bare coupling constant, the UV cutoff, and then we do we'll shown in the renormalization group and run the coupling, integrate out all the degrees of freedom between lambda naught and lambda, and get the coupling constant at the scale lambda. There are two cases to be distinguished. One is when the coupling constant C at 0 is C0 is positive. So when C0 is positive, the characters of the running of the coupling something like this. Coupling, I'm just drawing schematically, not to be thought of as something that's quantitatively accurate. The C, so this lambda, when lambda goes to 0, this logarithm becomes larger and larger, and C goes to 0. The coupling constant goes to 0 in the infrared. C goes to 0 in the infrared. Or if I try to extrapolate this theory to UV, this formula would tell me that there is a Landau pole that happens at lambda naught e to the power 2 pi over c naught. So the behavior is similar to quantum electrodynamics. That is, coupling constant goes to 0 in the infrared. We cannot define the theory all the way to the ultraviolet, there is a maximal cutoff at the scale of the Landau pole that we have to always impose on the theory. That is one situation. But if the coupling constants start as at a negative value, then the situation is very different. The coupling, if it starts at some negative value, it will blow up at a finite lambda. Lambda equal lambda naught e to 2 pi minus 2 pi over absolute value of C naught. Since C naught is now negative, I'm writing this way. Lambda naught exponents of e to minus 2 pi over C naught, and the theory seemingly would approach a strong coupling regime when the coupling constant, according to the solution to the one-loop beta function, goes to infinity. Okay. So now what is, yeah?
In relativistic QFT, sometimes we require the potential to be bounded below something.
A lot of time. So what's happening here is that the vacuum does not suffer from instability if you take C to be negative. And the reason is very simple. The number of particles is conserved. So one cannot we cannot go from the vacuum with psi equal to 0 to another state with non-zero value of psi. Since the number of particles, n, which is integral dx psi decker psi, is conserved, there is no way one can go from one vacuum to another. And since the theory doesn't have anti-particle, nothing can happen. Vacuum is a vacuum. There's nothing can happen with the vacuum. In fact, the fact that C naught goes to infinity like this has to be interpreted by looking at the system with more than one particle. Because again, one particle also can do nothing. Only when we look at two particles can we see something non-trivial that happens when C is not equal to 0. Okay, so what happens in the case when C equal to 0? So we have two particles. Let's consider two particles.
I'm going to say in more mundane terms, because this is just quantum mechanics. So what is the strong coupling scale?
Yeah.
Should have some more mundane explanation than the Schrödinger equation.
Yeah. That's the subject of homework. But roughly speaking, I'm going to sketch what happened here. And in the homework, you're going to reproduce exactly this exponential behavior. So we have two particles interacting with a potential that is a delta function. In fact, in order to make sense of this delta function in 2 dimensions, we have to regularize it. That is, we have to make the potential. So I'm drawing the potential V of R as something that looks something like this. It's not really, should not be really a delta function, but we have to regularize it so that the width of the potential is finite. It's 1 over, say, lambda naught is the width of the potential. Okay, so the potential has the height, negative height, and the height is equal to so the C naught, the coefficient of delta function, integral d2 x v of r is roughly speaking C naught, right? It's if V is a delta function, that would be the coefficient in front of delta function. So coefficient here is C naught divided by C naught times lambda square. Okay, so it's a delta function. Roughly speaking, it's a delta function. What we have seen in here is that in an attractive potential like this one form a bound state, and that can be confirmed by solving the Schrödinger equation of two particles interacting with the attractive interaction in 2 dimensions. Okay, two-particle quantum mechanics reduces a particle inner external field. So here you just need to solve the Schrödinger equation of a particle in an attractive potential. And for simplicity, one can take, for example, a square wave potential. Solve it. Now, this problem of a particle in a square wave potential is very familiar in quantum mechanics. If you do the problem in one dimension, you find that any attractive potential has a bound state. You just do, there's a bound state that doesn't disappear, which will make the potential weaker and weaker. In two dimensions, the same thing happens. It's always, there is always a bound state, even if the potential is extremely weak. It just needs to be negative, and then you get a bound state. The binding energy of potential of such a the value of the binding energy we have exponentially as a function of the depth of the potential, and reflecting this exponential behavior of the strong coupling scale in RG. Okay. Any question so far?
So here the physical question is what happens when P, the momentum going across, it's that scale, and you're saying you will see a bound state pole.
You see a bound state pole, yeah. In this scattering, the scattering amplitude in this theory actually can be computed. The 2 to 2 scattering amplitude can be computed exactly. And the reason is that because of the simplification due to the forward nature of the propagator, all we have to do is to sum up this latter set of diagrams. There's no other diagram that contribute, so that means that this diagram has to be put in the geometric series. It leads to a pole when the interaction is attractive, and there is no pole when the attraction, the interaction is repulsive.
Does that mean it's somehow integrable?
The potential?
Or is this somehow integrable, like it's like only 2 to 2 scattering? Like, you know, from...
You can just compute. There's no, because it's a quantum mechanics of it's a two-body problem instead of a many-body problem. It is just computable. Yeah, anyone with the...
Do the scattering amplitude of 2 going to n particle exist for n greater than 2?
There is no 2 particle going to n in quantum mechanics. 2 particle always go to 2.
Oh, because
number of particles is conserved.
Okay.
Yeah.
So there's no higher loop diagrams other than this ladder stuff?
There is no other diagrams than this ladder. And the reason again is that there is, what really happened is that our Hilbert space, again, the Hilbert space of quantum mechanics can be decomposed into direct sum of Hilbert space with 0 particle, with 1 particle, with 2 particle, etc. Once we set the initial state in the Hilbert space with 2 particles, all the intermediate state have to be 2 particles. So this diagram reflects this fact. Every cut goes through 2 propagators in the intermediate state, and there is no other possibility.
So this beta function is exact to all orders?
The beta function can be computed exactly if one specified what is the scheme of regularization. Yeah. So once you specify the regularization scheme, the two body problem can be solved exactly and get the exact beta function. Okay, so this is what happened in 2 dimensions, but as we have said, our main goal is to understand a class of theory in 3 spatial dimensions. Let's consider D equal 2 plus epsilon. So this epsilon, this trick of making dimension fractional is very familiar from the theory of second order phase transition. The beta function in D plus d equal 2 plus epsilon is simply equals epsilon times c plus c squared over 2 pi. The extra linear contribution comes from the fact that the operator psi decker psi has a dimension already in the naive dimension counting is already equal to minus epsilon, and so the coupling constant c has scaling dimension minus epsilon, so that's the reason why the beta function has an epsilon linear term here. Okay, so then let me draw the beta function. It's function of c. So it is quadratic plus a linear part. So it's 0 here and here. The beta function is equal to 0 at 2 points, c equal to 0 and c equal c star. So c star equal minus 2 pi epsilon. And the flow diagram looks something like this. This is the attractive point, and this one has one irrelevant. You have one relevant direction. Okay, so what we see is the following: if we are working near the point c equal to 0, the interaction psi decker psi is irrelevant. If we perturb the theory a little bit away from the point c equal to 0, it will flow back to c equal to 0, in consistency with the irrelevance of the operator. And that happens even for c that is large and positive, but when we make c negative and sufficiently large, we can reach another fixed point. That fixed point here is the point where the coupling constant remains constant along the RG flow. Physics seems to be should be a scale invariant at this point.
That's where it's just from bound state when the attraction is strong enough.
When the attractions are physically against, so this exactly what happened in dimension larger than 2. For example, in 3 dimension, if we solve the Schrödinger equation in a square wave potential in 3 dimension, there is a critical depth of the potential at which there is a bound state. And that critical depth is this value, should be assigned to this value.
So this result is non-perturbative then?
Then this result, if we...
It's not actual expansion, it's the exact.
It should be exact, yeah. Because the problem is basically quantum mechanics, this can be done also exactly. But at the level of the field theory, that's one way to see that the appearance of the non-trivial fixed point.
If you take epsilon negative and c positive, you get fixed point as well for positive c.
So if d, let's see what happened if d larger than d equal to minus epsilon. Okay, it's 2 equal minus epsilon. I think what will happen is that there is a minus epsilon c plus c squared over 2 pi. Then this thing here. Let me try to see what happened. This flow will be something like this. It's going like this. Okay, so what happened here is the following. In one dimension, one can think about the problem in one dimension. In one dimension, if we have bosons with repulsive interaction, C larger than 0, boson with repulsive interaction flow to non-trivial fixed point. Turn out that is just fermions, just spinless fermions. The 2 bosons, if they have very long wavelength, goes to each other, the wave function actually vanishes when they touch because of the repulsion. So effectively in one dimension, boson becomes, sometimes we say this word, boson becomes fermion. That one corresponds to the behavior of a free fermions. So if we go this way, then we go to formation of bound state. If there is a attraction. Yeah. Any question? Okay, so
for d equal to 2 plus epsilon, you found a fixed point, which is scale invariant. Is it also conformal invariant? Because number of particles are conserved. So if I take two operators with different number of size, 2-point function should vanish, right? So is it a conformal invariant theory as well, or is it?
So I'm going to discuss now what is the notion of conformal invariance in non-relativistic physics. Yeah, we can go into. So this is a motivation to consider theories with scale invariant. In relativistic theory, scale invariance often implies the conformal invariance, and we can ask whether there is a conformal invariance, that is the set of symmetries that is larger than scale invariance in non-relativistic theories. So that is what we are going to do now. So now the topics of this course, of this talk, non-relativistic CFT. First, we are going to talk about Schrödinger symmetry. That can be thought of as a non-relativistic version of conformal symmetry. And the way why it's called Schrödinger symmetry, because it is the symmetry of the free Schrödinger equation. If I write the same equation that I wrote before, d of dt, I think is equal minus over 2 m psi, and ask what are the operations that allows me to take one solution to transform it to another solution of a Schrödinger equation, I get the following transformation. So if I have a solution psi t of x, I can construct a new solution psi prime, which is equal to the old solution at the displaced position x plus a. That is the operation of translation. So I have translation, spatial translation. Similarly, I have time translation. So this is operator P, and time translation would be generated by the operator of the Hamiltonian H. Another trivial thing is to take psi prime equal e to the e alpha psi. That is the operator generated by the operator of the total number of particles. Let me call n. N is the operator that rotates the phase of psi. These all are familiar. Another familiar thing is rotation. So Mij, I'm not going to write. It's rotate space. X goes to x prime equal to rotated x. Oh, that's familiar, but in non-relativistic theory there is Galilean boost, which takes a solution to a new solution, which is equal to psi of t x minus bt, roughly speaking, but then I have to correct that by multiplying that by a factor which, if you have to check if the sign here is correct, but it's a phase factor multiplying to that function where x goes to x minus bt. The reason why we need this phase factor is very easy to see. If you substitute that into the Schrödinger equation, the time derivative can act on the second argument. It will spoil the Schrödinger equation if we don't have the this factor. So this, let's call that a Galilean boost along the I direction ki. So I have a Galilean boost Ki. It's not the Lorentz boost, but there's Galilean boost. Then there is that is usually all the symmetry of a non-relativistic system of interacting particles. But if we have free particle like this, we have dilatation. Psi goes to psi prime equal psi lambda square t lambda x 1 over lambda to the power of d over 2. That lambda square here and lambda square here. Get the equation still remains satisfied. Okay. I think here I might have missed some terms that look something like this, but I leave it for you to check. Okay, now the most non-trivial thing, and it makes the use of the word conformal symmetry somewhat justified, is the existence of something that I would call proper conformal transformation. Okay, turn out that if we have a solution psi of t and x, I can generate a new one by the following rule. I get psi of t divided by 1 plus alpha t, x divided by 1 plus alpha t, various factors here that need to be found. This factor is basically to ensure that the normalization of the wave function remain the same. I over 2. This one I'm not sure I get the sign right, but it looks like this. Turn out that there is such a transformation which keep the solution invariant, keep the equation satisfied.
Should we think of this as like the analog of a special conformal transformation in the time direction?
Yeah, it looks like what we are doing here with the time is inversion, translation in inversion. But what happened to space is not the same, right? I'm going to tell you a bit later how to connect this to the usual conformal transformation in relativistic space. But is there any questions so far? Okay, so
can you view this group as a contraction of the relativistic?
Yeah, I'm going to tell you a little bit later, but maybe I'll tell you now because this issue has arisen. How do we think about this? How do we relate this to relativistic? Can we get this theory, get this symmetry from relativistic conformal symmetry? Okay, so we can do the following exercise. So let me take the usual relativistic. So let's consider d plus 1 dimensional relativistic space, Minkowski space. Okay. And let's consider Klein-Gordon equation. Minus dt square plus dx square. So I'm going to write this, it's di plus d square over dx d plus 1. So I'm single out one particular last coordinate d plus 1 times phi is equal to 0. Here the sum over I is from 1 to d. Let me rewrite this equation in light cone coordinates. So I introduce x plus minus, and my x plus minus is going to be x0 plus minus x d plus 1. And I have to see whether I think I need to get over square root of 2. x0 is t. Right. So we have x0 here. So then the Klein-Gordon equation becomes like this. Becomes minus, if I'm not mistaken, d plus d minus plus di di times phi is equal to 0. And now if I required my field to have the form E m x minus times a function that is a function of only x plus and xi. If I'm searching for solution of this form, then this equation becomes simply the 2m with the minus d over dx plus di di phi x plus xi equal to 0. What we see here is the Schrödinger equation now, with m playing the role of the mass and x plus playing the role of time. So if I do a search of solution to the relativistic Klein-Gordon equation, it's fixing one light cone momentum to be m, the mass, then this equation that I got is the Schrödinger equation, which suggests that one can get the Schrödinger algebra of transformation by doing the following operation onto the algebra of conformal symmetry in d plus 1 dimension. The operation is to take, so let me erase this thing. The operator is to take this conformal algebra and select the generator that commute with one light cone momentum, say p plus. So I want to select every O that commute with one of the light cone momentum, which is one generator of the, as we know, one generator of the conformal algebra. If two of these, if we take two of these O1 and O2 that both commute with p plus, the commutator is also will commute with p plus. So we get a closed algebra as the result. And this algebra turned out to be the algebra of the canonical, of the standard Schrödinger algebra with the following identification. So here I'm drawing a translation table between generators of the usual relativistic conformal symmetry and the non-relativistic conformal symmetry. So this just a few of these items. Let's see.
So I have a question. So here
Yeah.
you're compactifying in the light cone direction.
Yeah, in the light cone direction.
So you're okay with the, well, polarity is gone. Doesn't it lead to any inconsistency of the theory?
I assume it will. Normally it will. Here we are just using that as a formal manipulation to get the algebra.
But I wonder if it can regard as a physical compactation one way or another. Maybe not.
I know that there have been attempts to construct this solution to string theory that realized configuration with on the boundary would have this this Schrödinger symmetry. So it might actually make sense in certain cases.
Well, this is the symmetries that you get in a relativistic conformal spacetime with a codimension 1 null plane. As like a defect, you can imagine a theory living on that defect, and you'd have this symmetry.
We have to have all this mode to have the same one of this p plus momentum. So I'm not completely sure what is the yeah. So what used, so is relativistic, and here is Schrödinger. What used to be p plus becomes the operator of mass, which is m times the number of particles. What used to be p minus becomes the operator of the Hamiltonian. Right, so that's the momentum. Translate to momentum. The operator d plus m plus minus becomes d in Schrödinger. So here the dilatation in Schrödinger space, in Schrödinger algebra, correspond to a linear combination of dilatation and boost along the plus minus direction. That's, and then there are various other things. So one thing that I'm think is m I plus becomes ki. One of these rotation Lorentz boost along the plus I direction becomes Galilean boost. And then what's non-trivial? K plus, I think K plus over 2. K plus over 2 becomes C. Okay, I didn't say what is C. C is the generator of that proper conformal transformation. Yeah. So this proper conformal transformation comes from one of the proper conformal transformation in the relativistic theory. The one along this, there are 4, this K mu, 4 conformal transformation, and only one of these along the plus direction commute with p plus, and that gives us the operator of the proper conformal transformation.
I'm sorry, what is Ki?
This is Ki is the Galilean boost. Yeah. This one. Sorry for the confusion in the notation. This is not the proper conformal transformation. This is a Galilean boost. Galilean boost very naturally is the Lorentz boost. It's some kind of Lorentz rotation, but along one direction is null, the other is spatial, and this one. And you can now be sure if you know how. Now you can actually get this formula from a more regular route. Just take the relativistic space and applying this transformation K plus, and then you get the non-relativistic transformation.
In this non-relativistic limit, as you mentioned, it's like green function have a pole, there's a really exact pole. But in general, on the relativistic conformal field theory, usually the correlation function don't have a pole, they have a branch because of conformal scaling dimension not integer. So yeah, it looks like there's a tension here. That is, I imagine the CFT probably don't have any pole, but we'll take this special Bicon limit. You get this, you make a situation to argue actually certain correlation function have a pole.
Certain correlation, yeah, has a pole, but as we will see, most of the correlation function in non-relativistic field theory do not have a pole. The the property of a very special operator that create one single particle that for the feature at least has a pole. But we will see there is an operator that creates two particles, and now this doesn't have a pole. The propagator has a branch cut. It's very similar in a way. It's very similar.
So maybe another question. This operator, the single particle operator in this non-relativism limit, do they correspond to certain local operator in the CFT, or they just don't appear?
Correspond to an operator with dimension equal to dimension of free operator.
Oh, so
yeah.
Very special dimension 3
yeah.
operator.
Dimension of free operator. That's the propagator which already has a 1 over p square.
Okay.
Yeah.
So
propagator.
With a high dimension CFT, like maybe some dimension 3 operators are very special. They have some special property. They have a pole actually.
Yeah.
So you're more interested in non-relativistic theories, but in order to recover this transformation, you have to resort to this light cone limit, which is not at all physically related to theories that you're going to consider. Is it possible to recover the same non-relativistic algebra performing non-relativistic limit from relativistic theory and see how it emerges there?
No, I don't believe it generically will be successful, because if we take a relativistic theory and take this usual non-relativistic limit, that is all particles are near the threshold of production, energy close to rest mass, generically that collection of particles interact in a way that knows about the scale, which is the mass of this particle. Yeah. So I don't think there is a way to do that, except for one case, maybe. That is the special case of anyons in 2 + 1 dimension. So in the case of particle with fractional statistics, I think one can get this by direct non-relativistic. I think, yeah, but maybe there is a subtlety there as well.
I have a conceptual question. So usually people appeal to conform field theory because it's you have to go around the RT flow, it's strongly coupled, and you invoke the symmetry to construct the theory. But here it sounds like you can actually solve for RT flow. So
in this particular theory, we can solve for RG flow.
It means that if you have different matter content, it's more difficult.
No, but even in this theory, we will see that although you can you know exactly there is a flow and the coupling runs, how the coupling runs on the flow, you don't actually know, for example, dimension of all the operator in the non-trivial fixed point. In the trivial fixed point, you have operator psi square, psi cube, etc. And now how this translate into a strong coupling fixed point, the dimension is going to be computable. We are going to see that it's exactly computable for charge 1, charge 2, and charge 3 operator. But starting from charge 4, there is no analytic calculation possible. Yeah, except if you resort to large n or small epsilon limit. Yeah, even for this, and presumably, if one. So this is this we are going to see. Okay, so in this way, this is one of the way to look at this algebra, but again, I think it might be the specific weakness of our education, that everything we do in non-relativistic theory have to be looked at from the relativistic point of view. I think the atomic physicists knew about this transformation long before us, and that transformation or similar things has been used in atomic physics to treat the problem of how the cloud of gas is released from a trap. That's a separate question. Okay, so now shortly about the Schrödinger algebra. We have I have listed all the the generators have outlined how the generators can be related to generator of relativistic algebra. So it just becomes a very mundane task of computing the commutators, the structure constant of the algebra. I'm going to just tell you a few facts. So N is a center. N and anything is 0. N is the operator of the number of particles. All the other operators are neutral with respect to this N. Another interesting fact is that the operator of so K is Galilean boost, and the momentum commute to I delta Ij times the mass. So M is equal M times N. Becomes the mass. That's an interesting thing. And what are the other interesting things? The P is equal I of P dk minus I of K dH equal plus 2 IH dC minus 2 IC. One more, maybe, then that's it. C and H. And there are some other things, but there's a whole table you can write down. So first of all, I want to bring your attention to the following thing. One can classify the operator by how it commutes with the dilatation. So momentum can be assigned dimension 1, and energy can be assigned dimension 2, as how they commute with the dilatation. Trans-Galilean boost, usually we don't think about the dimension of the Galilean boost operator with dimension -1. And this special conformal transformation at dimension -2. So other operator has dimension 0. For instance, its N has dimension 0. That's one fact. Another thing interesting is that this 3 operator, D, H, and C, form SO 2,1 subalgebra. That's another thing that it's also known within the atomic physics community. Okay, so any question?
I'm a little bit surprised that the Galilean boosts commute with the dilatation in the same sort of way as the other K generator that we normally think about. It looks like a special conformal generator at the level of that commutator. Is there an intuition for why that should be? Is it worth that
It's interesting. I'm not sure I understand that's because this table doesn't relate this K, relativistic K. Most of them has no counterpart in the other side. I think the way Yusuke and I chose this notation just because of that fact. It's just the way we choose this notation. Yes.
Right, but the commutation relations are
the commutation relations are very similar. So I'm not completely sure. Yeah, I understand that. Okay, any question?
It seems like the scale invariant part of this, like the first 3, get close. Is there any statement?
Which part?
Sorry, like D, P, D, K, and D, P, K, and H.
PK, but PK commute to this.
Sorry,
yeah.
M. If we just drop the C. Is there some theorem that tells you when, if you have like just the scale invariant part, it can enhance to the conformal?
Yeah. In principle, we can imagine a situation in which there is no there is only scalar invariance. But in the theory, at least of the type of the theory that we are considering here, I think it's almost inevitable. And let me try to first tell you how these operators are expressed in terms of creation and annihilation operator. So first in free theory first, and then we go to interacting theory. So in free theory, we know that all operator has to be constructed from this basic psi of x and psi decker of x. But I'm going to introduce operator that are bilinear in psi. First operator is a density, n of x is equal to psi decker psi. Each of that is computed at x. Another operator I'm going to introduce is operator j. J is the momentum density, is defined this way, minus I over 2 psi dagger grad psi, going this way. Okay, so I'm going to define two local operators at n of x, and the claim is that all these operator of the Schrödinger algebra can be written in terms of n and j. And one thing about this n and j is that they themselves form a closed algebra, and n commute at different points. J of x, n of y, let me see, commute to let me go in this way. N of x, j of y equal minus n a of y grad delta x minus y. And one can find that j and j also commute to itself. So let me write I and j is equal minus I j x di plus j I y dj delta x minus y. J form actually this J form a closed algebra by itself, and that algebra is the algebra of diffeomorphism of space. One can check that this J actually generate diffeomorphism, but J and N also form its own closed algebra. And the relationship with the Schrödinger algebra is encoded on how the operator are expressed in terms of this current.
But you're not claiming that diffeomorphisms are symmetrical.
What?
Because you mentioned diffeomorphisms, but we are not claiming that diffeomorphisms are symmetrical.
No, because Hamiltonian doesn't commute with this. Yeah, they just form an algebra, but normally Hamiltonian does not commute with this. Okay, so here's the algebra. So the number of particles, of course, is integral over x. The momentum is integral of j. Galilean boost turn out to be just integral of xi times n of x. Dilatation up to a factor of 2 maybe. I'm not sure if I get it right here. And C again up to a factor of 2. Let me see if I have it somewhere.
So is the first operator related to the dipole?
The operator of K is the in some theory we are associate that with the dipole symmetry. Now, normally the operator K do not commute with the Hamiltonian. It's the following. We can actually see how it is because the Hamiltonian commutator of the Hamiltonian with K is integral dx, then derivative of n, right? But there is a continuity equation. dt of n plus j is equal to 0. I set mass to 1, so it's actually then derivative with respect to n is x grad j. And then you can do integration by part. And what come out is the Hamiltonian the commutator Hamiltonian with Lorentz boost, Galilean boost is the momentum. So in this theory that in the normal non-relativistic theory, the dipole moment of the system is not conserved. And in this way, actually, you can compute all the if you get this transformation, you can get all the commutator of all the commutator between these operators.
This is the same in a relativistic theory with respect to ordinary proofs. And usually we say that K you can write as Tp plus the center of mass. The center of mass is conserved. So why is it? There's still some conserved quantity? It's just not K, right?
Yeah, if you include T here, the center of mass will be, if we have to add the T times, I think T times J something. Yeah. Here I'm doing commutator at equal time. Yeah, and then H will not commute with K. Yeah.
How can you also write the Hamiltonian as an integral over n and j?
No. Yeah, the Hamiltonian is something that has to be dealt with separately. And the Hamiltonian, but fortunately the commutator of the Hamiltonian with all this quantity, well, except for this, all this quantity can be obtained by appealing to the continuity equations, because the time derivative of n is expressed in terms of gradient of j, and so we get the commutator of h with respect to all of this. Now we assume that the theory is boost invariant, translationally invariant. H and p would be equal to 0. Okay, so that part is taken care of. The most non-trivial part is how the Hamiltonian commute with the dilatation. And that, of course, is the thing that distinguishes theory that is scale invariant from a scale theory that non-scale invariant. In a free theory, where the theory is scale invariance, H and D and H would be equal to that, and that can be obtained by writing H equal integral dx grad psi square over 2m, and then we can make sure we can check this. Now the claim is that at the critical point, at the fixed point, the same thing, the commutator of the dilatation and the Hamiltonian must be the same, and so the just scale invariance, D and H has to be equal to H. This is scale invariance. So in fact, if in the way that we construct this operator from the Psi-Decker, that if our theory, non-relativistic theory, is constructed from the operator of creation annihilation, maybe that's not the only way to construct the non-relativistic conformal field theory, but if that is the case, then all the Schrödinger algebra comes out from the scale invariance. Scale invariance would imply that there is a full Schrödinger symmetry. Okay, so any questions so far? When do I have to stop?
It's more basically the time.
around this time? Yeah, okay, so next time we will do more interesting physics. Thank you.